This is chapter 13 of Astronomy 100. The chapter is called Star Stuff. There's 4 sections in this chapter: star birth, life as a low mass star, life as a high mass star, and then stars in close binary systems. So we'll look at each of these 4 sections fairly quickly. First, take a look at page 328 in your textbook. You're going to see a pretty incredible picture of a star that is blowing up. It's releasing its heavier elements out into space, and at some point in time, those heavier elements might become part of another cloud of gas and dust that will eventually form a solar system. The picture was taken in different wavelengths of light, so you can see almost all of the matter that's being thrown off into space, which is rather incredible. So our goals for learning in this section are: how do stars form, and how massive are newborn stars? Newborn stars can appear in a couple of different ways in space. As you see over on the left there, here's a newborn star that is just starting to shine pretty brightly, but there's a cloud of gas around it, and so that illuminates that cloud. The cloud on the right looks dark, where some dust particles are blocking the light from more distant stars. So clouds of gas and dust around stars can give us some clue as to what's happening inside. Stars form in dark clouds of dusty gas in interstellar space. That area is called an interstellar medium. So remember the forces we've talked about before in dealing with planet formation, solar system formation. Well, now it has to do the same thing in star formation, where gravity and pressure are the 2 variables that will dictate just what's happening with a star. Gravity can create the stars if it can overcome the pressure, outward pressure of heat, and gravity within a contracting cloud becomes stronger as the gas becomes denser. So it's almost like an accelerating process. The closer the particles get, the more gravitational attraction they have. The closer they get again, the more it has. So it sort of accelerates as the particles are coming together. A typical cloud of molecules of gas might be as low as 30 kelvins, which is extremely low, slightly warmer than what might be found in interstellar space. And it might contain a few hundred solar masses of dust that gravity eventually pulls together. The cloud prevents pressure buildup by turning some of that heat energy into infrared and radio waves, and they escape the cloud. So gravity is kind of king here, where it's pulling the particles inward. One of the things that's interesting is being able to see how this can be simulated with a cloud containing so much mass coming together and eventually starting fusion. The process might be random, where the motion of the molecules is all over the place, so the gas cloud actually becomes somewhat lumpy. And then in the next phase, there are places where you can have a whole cluster of stars if there's enough gas and dust, or if it's a smaller cloud, you get 1 star out of the fragmentation. As stars begin to form, the dust grains that absorb the visible light will heat up and emit infrared light. So there might be a star somewhere in this cloud that's actually illuminating the gases in front of it. We can get some long infrared light shining from these regions where stars are forming. So that's an indicator of a star birthplace, is long wave infrared light. Solar system formation is a good example of star birth. We've talked about solar system formation in the past, where a cloud of gas and dust coming together forms planets and a star. We'll take one individual star, basically goes through the same process, with the gas cloud being large and diffuse, and then as particles come closer and closer together, conservation of energy dictates that those particles start to spin. So the cloud heats up as gravity causes it to contract due to conservation of energy. Contraction will continue if the heat energy is radiated away. And again, that's called the conservation of angular momentum. So it begins to spin faster and faster. It also flattens because of the collisions between the particles. So we naturally get a disk of particles spinning faster and faster and closer in. The spinning cloud flattens as it shrinks, and that rotation will actually cause jets of matter to shoot out along the rotation axis. So we see kind of the waste product of this spinning action with these jets of gas. Here's an actual example. Two jets of material being shot out in opposite directions by this protostar. The flow of the jet to the left and to the right is from the protostar forming in the middle. Here's another example where we have this disk of greenish material. There's apparently a protostellar disk which will eventually form a protostar and then a star, and then the flow of jet material is out the left and the right. So a protostar contracts and heats until the core temperature is sufficient for hydrogen to fuse. In other words, nuclear fusion. Contraction ends when the energy released by the fusion balances the energy radiated from the surface. So again, we hit that balance where radiation pressure is balanced only by gravity, and hydrogen fusion is taking place in the core. That's an interesting statistic, though, that it takes 30 million years for a star like the Sun to actually form. So here's the summary. Gravity causes the gas cloud to shrink and fragment. The core of the shrinking cloud heats up. When the core gets hot enough, fusion begins and it stops the shrinking. And then a new star achieves a long-lasting state of balance. And as we learned this past week, that balance is where we put the star on the HR diagram. That's the main sequence. So how massive are newborn stars? Well, we have these little circles here on the letter B side of the picture that shows where we have possibility of brown dwarfs in the constellation of Orion. Apparently they're giving off a heat signature which is certainly less than that of a real star. A cluster of many stars can form out of a single cloud, so the cloud must be very, very large in order for lots of stars to form from it. Very massive, as you can see by the diagram here, very massive stars are rare. Low mass stars seem to be more common. At least that's what we found in the survey of the skies. So in the diagram here you see from between 0.08 solar masses, sun masses, and 0.5 sun masses, we have 200 stars. Between 0.5 and 2, 50 stars. Between 2 and 10 solar masses, 10 stars. And only one star that might be between 10 and 150 solar masses. So the relative number of stars definitely decreases when you're looking for more massive stars. So what's the upper limit? Well, there's radiation pressure that's of course pushing energy and particles outward. There's gravity pulling it all together. But observations haven't found any stars more massive than about 300 solar masses. That would be the largest. So fusion won't begin in a cloud if some sort of force stops contraction before it reaches about 10 million Kelvin. That's 10 to the 7th. Thermal pressure can't stop contraction because the star is constantly losing heat energy from its surface. So what's another form of pressure that can stop contraction? Well, it's called degeneracy pressure. Something dealing with quantum mechanics, where you basically have the atomic structure of hydrogen and helium, and the electrons that actually orbit hydrogen and helium nuclei not being allowed to occupy basically the same place at the same time. So we have this limit, this natural limit that would allow a star to only reach a certain size. So we have thermal pressure, we also have degeneracy pressure that are factors in the formation of a star. So degeneracy pressure halts contraction of objects with something less than 0.08 solar masses. So it can't become hot enough for fusion. We end up with an object called a brown dwarf. Brown dwarf gives off infrared light because it's heat left over from contraction. You push something together so tight, it's going to generate heat, but it's not heat from fusion, it's heat from contraction. So its luminosity gradually declines as it loses its thermal energy and just becomes basically a big chunk of rock floating around in space. So these infrared observations can reveal recently formed brown dwarfs because they're still relatively warm and somewhat luminous, although we wouldn't be able to pick them up even with a small telescope. Stars more massive than 300 solar masses would blow apart. They'd explode. They just can't keep that much mass together. So stars less massive than 0.08 suns can't sustain fusion. Anything greater than 300 solar masses would simply explode. So these are the natural limits of star mass. So we've learned that stars are born in cold, relatively dense molecular clouds. And as a cloud fragment collapses under gravity, it becomes a protostar, sometimes a cluster of stars, surrounded by a spinning disk of gas. And then the protostar may also fire jets of matter outward along its poles. How massive are newborn stars? Well, they're always under 300 solar masses because radiation pressure would blow them up. And they have to be anything less than 0.08 solar masses would be a brown dwarf because fusion would never begin. In section 13.2, we're going to look at life as a low-mass star. As you see on page 335, a low-mass star is a star which has less than about 2 solar masses of material. So our sun is considered a low-mass star. Intermediate mass stars are somewhere between 2 and 8 solar masses, and high-mass stars are anything greater than 8 solar masses. So in this section we're going to look at what the life stages of a low-mass star is and how does a low-mass star die. This is probably the best way to show what happens to a low-mass star. Like our sun, which is 1 solar mass in size, so it's categorized as a low-mass star, we see that it tends to rise up slightly in luminosity, then it tends to cool down. In other words, it goes to the right and turns into a subgiant, and then it jumps up in luminosity, maintaining about the same temperature or a little bit less, and turns into a red giant. And it does that because it's basically run out of hydrogen, or it's close to running out of hydrogen fuel. It has a helium core. That core gets bigger and luminosity increases because the thermostat's broken. So the fusion rate doesn't stop the core from contracting. So helium is something that is going to start fusing in this particular case. And as helium fuses, we get, in this diagram, we get 3 helium nuclei forming 1 carbon nucleus and releasing a lot of energy. Because 2 helium nuclei don't fuse, 3 helium nuclei do. That's what gives us the carbon. But a lot of energy is still produced. So the thermostat's broken in a low-mass red giant because degeneracy pressure supports the core. The core temperature rises rapidly, helium fusion begins. And then helium fusion rate skyrockets until the thermal pressure takes over and expands the core again. So the star is fluctuating because of this increased amount of helium in the star. Helium core fusion stars neither shrink nor grow because the core thermostat is temporarily fixed. As you can see in the diagram, the hydrogen is now surrounding the helium in this particular case. The hydrogen is forming a shell around the helium, and with much more helium, helium is fusing to form carbon. So this HR diagram shows the entire process, going from a red giant phase to a planetary nebula, in which case you see it going straight across and to the left, so it maintains its luminosity, but it gets hotter because of helium fusion. And then ultimately, as fusion begins to lessen, it swings down and to the right, finally becoming a white dwarf. And observations of star clusters agree with these models. Helium core fusion stars are found in the horizontal branch of the HR diagram. So we see subgiants and red giants as part of the process of low mass star dying. Here's a good example of a low mass star which is in the process of dying. Nova, it basically explodes, throwing material off into space. And what's left then is a white dwarf in the middle. So after the core helium fusion stops, helium fuses into carbon. We get a carbon core star, and this double cell fusion stage never reaches equilibrium, so we get pulses of heat, thermal pulses as they're called, and which with each spike, convection brings more carbon up to the core, transports it to the surface. So the element carbon is, at least what we've seen up to now, is only the product of helium fusion. We see it in no other place in the universe. Double cell fusion ends with a pulse, ejects the hydrogen and helium into space. We call it a planetary nebula, but there's no planet involved. This is just one of the latter stages of the star's life cycle. So the core left behind becomes a white dwarf. It ends with a pulse, ejecting this material into space, as I said, and this is just another example. This is called the butterfly nebula. So fusion doesn't progress any further in a low mass star. The core temperature never grows hot enough. Degeneracy pressure supports the white dwarf against gravity. So we just have a very small whitish colored star, very, very hot, burning the heavier elements. So again, this is the entire life cycle as a star the size of our sun. Leaves the main sequence, turns to a subgiant, then to a red giant, then to a double shell fusion red giant. Throwing material out, it becomes a planetary nebula, and then very quickly drops down to the lower right, becoming a white dwarf. So, what are the life stages of a low mass star? Well, we get hydrogen fusion in the core. That's when it's on the main sequence. Hydrogen fusion in a shell around the core. That's a red giant stage. Helium fusion in the core. That's on the horizontal branch. And then double shell fusion. That's when it becomes a red giant. And finally, the ejection of hydrogen and helium in a planetary nebula leaves behind a very small fraction of original material, becoming what's called a white dwarf. Now let's look at life as a high mass star. Obviously, any star that is in our universe is burning hydrogen, but a more massive star will burn that hydrogen at a higher rate, possibly ending up with a different endpoint as it finishes up its life cycle. So what are the life stages of a high mass star? How do high mass stars make the elements necessary for life? And how does a high mass star die? We're going to look at all of these life stages. This element cycle is a bit different from a low mass star. High mass main sequence stars fuse hydrogen to helium at a higher rate. They use carbon, nitrogen, and oxygen as catalysts. So those three elements are contained in a high mass star and help to provide an accelerated rate of fusion. So a greater core temperature enables hydrogen nuclei to overcome greater repulsion. So the star is more massive, it's burning hotter, but it's also burning uh, different elements within its core. It's still nuclear fusion, though. So late life stages of high mass stars are similar to those of low mass. We have core fusion, that's on the main sequence again. We have hydrogen shell fusion as a supergiant, not a giant, but a supergiant, and then helium core fusion as a supergiant. So instead of hydrogen going to helium and possibly carbon, a higher mass star, because of its higher mass, higher gravitational pull, higher temperature, enables the star to create or generate heavier elements. Here we have carbon and helium combining to form oxygen, oxygen and helium to form neon, neon and helium to form magnesium. These are only elements that are found near the death of a high mass star. So the Big Bang made about 75% hydrogen, 25% helium. Stars are able to make everything else by the accelerated fusion. Helium fusion can make carbon in low mass stars, but the CNO cycle can change carbon into nitrogen and oxygen. And of course, we rely on oxygen for our breathing here on Earth. So the high core temperatures allow helium to fuse with these heavier elements, and we get these heavier elements as a result. And here's some other reactions. Oxygen and carbon forming silicon, oxygen and oxygen forming sulfur, silicon and silicon forming iron. So core temperatures in stars greater than 8 solar masses allow the fusion of elements as heavy as iron. And these are places where we can see those on the periodic table. So obviously they're behind, or I should say, larger elements, larger atomic structures than carbon, nitrogen, and oxygen, which are 6, 7, and 8. They're lower down on the periodic table, which means they are heavier elements. So advanced nuclear burning proceeds in a series of nested shells. Instead of a helium shell or a hydrogen shell and a helium core, we get a multiple of layers within it, as you can see here. Hydrogen, helium, carbon, silicon, oxygen, neon, magnesium. But iron is a dead end because nuclear reactions involving iron do not release energy. So iron has the lowest mass per nuclear particle. So in most cases, iron is the farthest an element can be fused into. So how does a high mass star die? Well, remember degeneracy pressure. It goes away because electrons combine with protons in this case, and they make neutrons and neutrinos. So here we get the actual production of another subatomic particle from protons and electrons. We get neutrons. The neutrons collapse to the center, forming what's called a neutron star. And that also results in a supernova explosion because the resulting or the remaining energy is thrown out into space in a huge, huge explosion. So this energy and neutrons released in a supernova explosion enable elements heavier than iron to form, including gold and the heaviest naturally occurring element, which is uranium. Uranium has an atomic number of 92. So it has 92 protons. That's the heaviest element nature can make from a supernova explosion. Anything higher on the scale, such as neptunium or plutonium, as you see starting at 93 and 94, those are artificially created elements, man-made elements, as some people say. So the supernova remnant is what you see here is this colorful cloud. Energy released by the collapse of the core drives outer layers into space. Here's an example of what's called the Crab Nebula, which is a supernova remnant. It was first observed in the year 1054. Here's another example of a supernova called supernova 1987A, where we see the star before it blew up and then after as a supernova on the right side. So a star's mass determines its entire life story because it determines the core temperature. High mass stars have short lives, eventually becoming hot enough to make iron and end in supernova explosions. Low mass stars have long lives. They never become hot enough to fuse carbon nuclei, and they end up as white dwarfs. So, life stages of a low mass star: main sequence, red giant, helium core fusion, double shell fusion, and then planetary nebula, which eventually results in a white dwarf. A high mass star is one where it's on the main sequence, turns to a red supergiant. We get helium core fusion, we get multiple shell fusion, and then a supernova leaves behind a neutron star. So what are the life stages of a high mass star? Well, they're similar to life stages of a low mass star, but higher masses produce higher core temperatures that enable fusion of heavier elements. So only a high mass star can generate the higher atomic number stars. How does it die? The iron core collapses, leading to a supernova. This last section has to do with stars in close binaries. So the goal is, how are the lives of stars with close companions different? In other words, binary stars. Here's a section that shows basically what happens in an artist's view. We have two stars, which one is larger than the other, but because of the gravitational attraction of the larger star, it appears that some of the mass of the smaller star is being drawn away. So the binary star called Algol is a 3.7 solar mass star, and the subgiant next to it is a 0.8 solar mass star. So what's strange about the pairing? How did it come about? Well, stars in Algol are close enough that matter can flow from the subgiant onto the main sequence star. So as you can see, one star's getting larger due to the loss of mass of the other. The star that's now a subgiant was originally more massive, but as it reached the end of its life and started to grow, it began to transfer mass to its companion, which of course is the larger star, and now the companion star is more massive.